I don't know what I'll do with it, but I'll record this in case anybody
Okay.
wants to listen to it.
I would, yeah, if that would be helpful
Okay,
for me down the road.
so let's talk about section 1.1 and its intro to limits. And I'm not going to go through like the whole thing
Right.
because we just really don't have time. Intro to limits. And maybe I'll, if you have questions, I can answer questions, or um, I'll just pick a couple problems in here. So the big thing, one of the big things in this section says that I don't really know how to write on this limit, like some of the notation we'll be using, the limit as x goes to c of some function f of x is equal to L, and this is a definition of limits that you have in the book. If and only if and only if the limit as x goes to c, and then I'm going to put this little minus sign there. That means from the left of a function, if the limit from the left is equal to L, and the limit as x approaches c from the right of a function is also equal to L. So that's kind of our definition of a limit. And so what does a limit mean? Like for example, like let's say that you have this function. I'll write it in function notation. So let's say you have f of x is equal to y. No, that doesn't make any sense. Oh, okay, that's cool. I just used the eraser. So let's say you have a function f of x is equal to x. That's what I meant to say. So it's like it's the line y is equal to x. Like if you were going to graph that, like when x is 1, y is 1, x is 2, y is 2. So it's like this line that goes through the origin, right? So if you were asking the question, what is the limit as x goes to 2, let's say, of our function. And what we want to find out, what we're looking at here is our y value. When I'm talking about a limit, I'm talking about what is the y value. This is our x value, and the thing that this is equal to is always going to be a y value. This is going to be a y value here. So if we're looking at the x value being 2, like here's 2, what is our y value equal to? And we're looking at things that are getting close to 2. We're not necessarily looking at x being 2 all the time, but we're looking at what happens as x gets close to 2. So as we move like maybe along the x-axis and we go to 1 and then 1.5, like 1.7, 1.8, as we get really close to 2, our y value is also getting close to 2, right? Does that make sense? Oh, no. Did I lose me? Okay. Let me pause this. Okay, can you still can't hear me, Ryan? Okay, what about now? Can you hear me?
I can hear you now.
Okay.
There was something wrong on my end.
Okay.
Sorry.
So I was just talking away and you couldn't hear me?
I was like, well, I know it's being recorded, so
Okay.
okay.
All right. So I was just saying, like, the thing here, when we're looking at this limit, this x values, these are the x values. And then the thing that the limit, when we take the limit, is the y value. So if we're looking at this function when
Mhm.
x is 2, getting close to 2,
Right.
or what is our y value? What is our y value equal to? And you can see here that the y value is going to be equal to 2. So that's what we're talking about when we're talking about.
Mhm.
And in order for this limit to exist, we need the value as it approaches like 2 from the left, and the value of y as it approaches 2 from the right. Like from the left, here's from the left, here's from the right. They both have to be
Okay.
approaching 2. Both of those values have to be approaching 2. All right,
Okay.
so let's see if I want to insert maybe a blank page here. Okay. Let's look at an example. Maybe if like some of the examples are going to be just kind of what I just did. Like let's say x is approaching -2, and let's say our function is x squared plus 7x plus 9. So this is a
Okay.
function, this is a parabola. If we would draw it,
Mhm.
maybe it would look, something like this. And it's just saying when x is -2, like what is going to be our y value of the function? When x is -2, what is our y value of the function?
Ah,
And it just means as we're
okay.
getting close to -2, it doesn't always have to be exactly -2, but just as we're getting close to it, we're looking at getting close to it. Maybe we're looking at -1.5 9 or negative 2.01 or something. But the first thing that we always try to do is just to input that number into the function and just see if it works. Like if we input negative 2,
Oh,
we just have
okay.
negative 2 squared plus 7 times negative 2 plus, that should be a negative, plus 9. And then we're just going to calculate what that is. So that's 4 minus 14 plus 9. So negative 10 plus 9. So negative 1. So we're just saying
Okay.
when x is getting close to negative 2, like what is our y value going to be equal
Okay.
to? So that's just a really simple example because you're just inputting that. And you're always going to try to do that, but sometimes you're not going to be able to do that. And I'll show you an example here of when you can't necessarily do that. Let's see. What if we have, like, for example, the limit as x goes to 0 of 4 plus x squared minus 16 divided by x. So you can see that you can't plug 0 into this function because you
Right.
can't divide by 0. So we have to figure something else out. We're going to either kind of look intuitively at what's happening in this function, or we're going to try to maybe do a little algebra on it. This one we can do a little algebra. So we're going to say the limit as x goes to 0, and then we're going to distribute this, or FOIL the 4 plus x squared. We FOIL it, we
Okay.
get 16 plus 8x plus x squared minus 16 in the numerator divided by x in the denominator. And I'm going to be talking fast and going fast, and I'm hopefully recording
Okay.
this. It says it's recording, so you can
Yeah,
see
yes, on my end too.
that. So we have the limit as x goes to 0. And then the 16s are going to cancel. And we have 8x plus x squared in the numerator and x in the denominator. So we can factor out an x in the numerator. And we have 8 plus x left in the numerator divided by x. The x's cancel, which is what we want to happen. And now we have the limit as x goes to 0 of 8 plus x. And it's okay that we
Okay.
canceling these x's. It's okay to cancel because x can't be 0 anyway in the beginning. So we can
Mm-hmm.
cancel those out. And then now we can just take the limit as normal. Like we can try and plug that x in, and then the value of our function, our y value, is going to be equal to 8. So that's what our limit is going to be in this example. Okay, does that kind of make sense a little bit?
Yes. Yeah, it does. And it's I have taken some pre-calc, so it sounds familiar.
Okay.
So that's good. That's good.
Yeah, that's good.
I'm just not an expert, but yeah.
Yeah, we can look at like another example. I kind of like this graphical method. Let me just draw a graph real quick, and then it just kind of helps to make sure that you can understand things. So let's say like let's say this is 4 and this is 2, and let's say this is negative 2. I'm just going to draw like a quick graph here.
Okay.
Let's put an open circle here, and then we'll go here. Let's say this is 2 and this is 4. And then I'll put a closed circle here just to draw some like weird graph like that. So
Mm-hmm.
then if we want to understand like the concept of a limit, I could write like what is the limit as x approaches 0 from the left of our function f of x. So when we're talking about a limit, remember if I'm asking for a limit, I'm looking for the y value. This is our x
Mm-hmm.
value. This is our x value. And then we want to find out the y value. This is going to be a y value. So
Okay.
our x's are approaching 0 from the left. So it means we're looking at wherever the graph is, we're coming close to 0 from the left, from the direction of the left. So
Okay.
like at first we're up here on this part of the graph right here. We're getting really, really closer, closer to 0. Like what's happening when we get close to 0 from the
For
left?
the if you approach it's the as you get closer to as you uh, as so as x approaches 0 from the left,
Yeah.
it hits about -2.
So we're getting
Or
close because 0 is over here, right? So we're just getting
mhm.
closer to 0. Like here would be our x value, our y value when x is right here. And like maybe when
Mhm.
x is -1, our y value is
Oh,
here. Like this would be -2, this would be -1. Maybe this is
okay.
-1/2. But
Okay.
as we get all the way to 0, what is our y
Mhm.
value?
Oh, I see. Okay,
So
4.
our y value is going to be 4, right?
Okay. Yes.
Let's
Yes.
look at another one. Limit as x approaches 0 from the right of f of x. So now
Okay.
we are approaching 0 from the right-hand side. So we're getting really close to 0. So we're now no longer using the same part of the function that we were using before. We're using this part of the function here.
Okay.
So
That
like when
makes
x is 4,
mhm.
our y value is here. When x is 2, our y value is here.
It would
What is
be
our
at -1.
Yeah, exactly. So because
Okay.
those two things are are not equal to each other, when we say the limit as x approaches 0 of f of x, since it's from the left it's 4, from the right is 0, it's -1. They're not equal to each other. This does not
Okay.
exist. This limit does not exist because the limit from the left of the function is not equal to the limit from the right of 0.
Oh, okay.
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 All right, so that's just a really super brief synopsis of section 1.1. Did you have
Okay.
any questions about that?
No, this was a a good explanation.
Okay.
It makes sense.
All right, then let's look at the next section real quick.
Okay.
Okay, so all right, so then we have section 1.2, and that's our limit theorems. And I would really encourage you to look over these limit theorems. They're on page 68 in your textbook. And it's just kind of the rules about limits and things that you can do with limits. And one of your discussion board, I think one of your discussion boards, you have to use these main limit theorems for. But I'll
Okay.
tell you about a couple of them, just again to give you a feel for them. The
Okay.
first
And
one,
I'm looking at them in the
oh, okay, good.
textbook.
So the first limit theorem says a limit as x approaches c of k. And that's saying that k is going to be a constant. So maybe k is 4. So I'll just do that. I'll say like the function is 4. That means that our function y or f of x, it's like f of x is equal to 4. That would be the function. So that function is just
Okay.
going to be a horizontal line, like y is equal to 4 is just going to be a horizontal line through 4, right?
Okay.
So if c is any number as x approaches c, like let's say we can make it any number. I could say as x approaches 1 of this function. So as we get really close to 1, as we get really close to 1
Mm-hmm.
from the left and from the right, what is the value of our function? The y value.
4
It's equal to 4.
is mhm.
So that's why they're saying the limit as x approaches c of k is equal to k.
Okay.
That makes sense? The limit as x approaches any number c
Yes. Yes.
of k
The
is
x value is going to be a constant. Yeah,
Yeah, the x
it's not
value
going
is
to
just,
change.
it can be any number. The x value could be any number.
Hmm.
This thing is going to just stay the same. So as x
Yeah.
approaches any number.
Okay.
All right, and then the limit as x approaches any number c of x. So that was kind of the one that I did in the beginning, one of the very first examples. This is our
Hmm.
function. This is our function now. The function is y is equal to x. So I graphed that one already.
Hmm.
So y is equal to x, or f of x is equal to x. That's the function. That's what this function looks like. Um,
Okay.
so if you pick any value of c, like let's say that c is 2.
Okay.
So if x is equal to 2, what is their y value?
Uh, 2.
It's going to be 2. If x was equal to 3, the y value would be 3,
Hmm.
and so on. So that's our second limit theorem. As x approaches any number c, for this specific function x, the function is x, that's always going to be equal to whatever c is. And then
Okay.
if you take a look at the rest of those, I'm not going to write those limit theorems out,
Mhm.
but they just
Yeah.
basically tell you that if you're taking a limit of a sum of two functions, you can separate it into two limits. The limit of f of x plus the limit of g of x.
Okay. Okay.
So it just
So
tells you that you can separate those things.
would they be graphed as separate
Um,
functions? Or I mean, I might be getting into the weeds with that question.
well, in the beginning, when you're talking about adding them, then
Hmm.
you would literally be adding those functions, whatever they were. Like if it was two parabolas, you could add them. But if you're finding the
Okay.
limit, you can separate those into two separate limits. And so if you did add them together and found the limit, you'd
Hmm.
get an answer. And if you separated them and found the limit, you'd get the same answer when you added them together.
I see. Okay.
And then
Okay.
it works for subtraction, and then multiplication works the way that you would think it works. You could just separate them as a product of two functions. So you could find the limit if you multiplied those two functions and get an answer, and then you could find the limit of each function, get those numbers and multiply them and you get the same answer.
Oh, okay. Okay, that makes sense to me.
And then division works the way that you would think. You can separate it limit of f of x on the top, limit of g of x on the bottom. The, rule number 8, that exponent it's on the outside of the function in the beginning, and then you can put it on, it just does on the function in the beginning, but you can also find the limit and then raise that limit to the exponent, and that's the same, you get the same answer as well.
Okay. Okay.
All right, so let me look for an example here. Maybe we can do. Um, I don't know if we want to do an example here. They're kind of straightforward. A
Yeah.
lot of it is algebra. There's some algebra.
Hmm.
I actually might skip this
That's that's
section, I
okay.
think.
I feel comfortable with the explanation you gave me as a kind
Okay.
of springboard.
And this is just
Um,
getting you used to those properties and just kind of playing around with some of these problems a bit.
I see.
Um,
Okay.
all right. So actually, I called that section 1.2 here. I said it was 1.2. It's actually 1.3. Remember, we skipped 1.2.
Hmm.
So this was section 1.3. And
Okay.
then let's take a look just maybe at some highlights of section 1.4. Section 1.4, we're continuing with limits. And this is of trigonometric functions.
Hmm.
Okay.
Yeah, yeah, I'm on 73,
Okay.
page 73.
Um, all right, so that one's pretty straightforward. Okay, let's do this one. Let's say we have a limit as x approaches 0 of sine of x over 10 times x. So don't be tempted to like cancel the x's here because you always have to take a sine of
Okay.
something. You can't just cancel an x and just have sine left. You know, that would be a sin, right?
Oh, I see.
Can't
That
do
makes
that.
that makes sense.
So you can't, even though it might be tempting to do that, you can't do.
Yeah.
All right, so then the first thing that we always want to, well, we always want to try and plug 0 in, right? But what happens when you plug 0 in?
Hmm. You end up with zero. Well, yeah, it's not a function if it's,
Yeah, you can't have that 0 in the denominator. You can't divide by 0. So that's
yeah.
a problem. So we can't do that. We can't just plug the 0 in. We can't divide those x's out, cancel those x's out anyway. But one thing that we
Okay.
can do is we can pull that 10 out to the front because that's a constant, and that those
Mm.
properties in the last section said that we can do that. May not help us that much, but we can pull it to the front and do this, and then write this
Okay.
as the limit um, as x goes to 0 of sine of x over x. And it seems like it still might not help you that much, but there's a property,
Hmm.
I think there's a property in your book. Actually, let me see for sure. This is section 1.4. Let me look real quick to see if there's something in your book that tells you
Okay.
what that thing is equal to. So that sine of x over x, whenever you see that, it's always going to be equal to 1. It should say that.
I see.
Do you
On
see it?
page
Oh,
75, theorem, there's a sign of t over t equals 1.
yeah, that's the exact same thing.
Okay.
It's also on page 72, right before the homework set. So this thing
Okay.
here is always going to be equal to 1. Sine of x over x. So we like to try to get our limits to be that, because then we know that whole thing is going to be equal to 1. And then this
Okay.
limit is going to be equal to 1/10, because we have 1/10 times that 1.
Times. Okay.
So that's just a
That.
property that's good to know.
Okay.
And let's see, what else? Hmm. I could do this problem here. The limit, let's say, as x goes to 0, of the sine of 2 times x plus 8 times x divided by x times the secant of x. So first of all, let's see. Let's do, because the problem is if we plug 0 into the denominator again, the denominator is going to be 0. So that's a
Mhm.
problem. So we know that we have to do
Okay.
some algebra or try to do something with this. So maybe
Hmm.
one thing that we might see is that you can actually do division on this thing, because if you have, remember, if you have a sum of something divided by something in the denominator, that's equal to a divided by c plus b divided by c, right? So that's
Okay.
just
Yes.
division. So let's try and do
Hmm.
that here. Do that same division. So we have sine of 2x divided by
Okay.
x.
Mhm.
Mm, divided by x secant of x plus, and then I'm going to separate this using those limit. Can you still hear me?
I can.
Okay.
Yep.
Um,
Can you hear me? Okay.
yeah,
Okay.
I just got like really quiet.
Okay.
8x over x secant of x. All right, so just following that basic rule of division. It's like adding fractions in reverse. All right, then let's do a little bit more algebra if we can. So we have sine of 2x divided by x, and then secant of x. Secant is the reciprocal of cosine.
Uh,
So
okay.
cosine, because cosecant is sine and secant is the reciprocal of cosine. So it's the same thing as x times 1 over cosine of x, right?
Okay.
Because that's what
Right.
secant is. Plus the limit as x goes to 0 of 8x over the same thing, x times 1 over cosine of x. Okay?
Okay.
And then let's see what we can do with that. Because we're trying to see if we can get it to look like sine of x over x, or just trying to get something where we can
Hmm.
take a limit where we don't have 0 in the denominator. So let's say this is equal to the limit as x goes to 0 of, um, in order to clear this fraction here, I could multiply the top and the bottom of this fraction by cosine of x. So I'm going to just multiply by cosine of x and then multiply this
Okay.
denominator by cosine of x just to clear those fractions. So in the
Okay.
top I have cosine of x times the sine of 2x. And then in the denominator I just have x, right?
Okay.
I
That
just
makes
have,
sense.
I'm dividing by this x. And then for the second one, limit as x goes to 0. And then I'm going to do the same thing, multiply the top by cosine of x, multiply the bottom by cosine of x. So in the top I have,
At 8x times cosine of x over x.
correct, okay.
Okay.
This one we can cancel these x's because it's 8 times x times cosine of x. So we
Okay.
can do that. The first one you can't cancel those x's because remember you have to have the cosine of something and the sine of something. So you can't cancel anything there. But what we do have, let's see. Sine how can we fix this? Okay. So we almost have something right here that looks like the sine of x over x. It almost looks like that. If I do this, if I write the limit as x goes to 0, and then let's say that I multiply the top and the bottom by a 2. So I'm just going to multiply the top and the bottom by 2. Then I would have 2 cosine of x over x times sine of 2x. Oh, some dog's not happy over there.
Yeah, sorry that.
That's okay.
Okay.
Dog,
Okay.
okay.
I gotta go.
Okay.
I'll see if my husband can let them out. I'll be right back.
Okay.
Hey, Justin. No. Okay. Okay.
Okay. So I think it's back. All right. All right. So then all I did is I multiplied the top and the bottom of that fraction by 2. And then I have this thing that is going to be equal to a 1. Because the sine of x over x is 1, the sine of 2x over 2x is going to also be equal to 1.
Okay. Okay.
And then let me just write the second one in. We have 8 cosine of x, just 8 cosine of x is that one. Okay, so now we know that this thing is equal to 1. Now we can, no, we can't plug a 0 into that thing. What do we do with that? No, I don't need 2 x's here. It should just be over 1. That makes sense then.
Okay.
Because yeah, I can't put 2 x's in there. There was only 1 to begin with.
Yeah. Okay. I was wondering about that.
Yeah.
So that helps.
So let's plug the 0 in then. So we have 2 times the cosine of 0 times this thing here is equal to 1 plus, and then for the second part, let's plug a 0 in, and we have 8 cosine of 0. And then cosine of 0, cosine of 0. Do you remember what cosine of 0 is? Like, the angle 0 would be right here. And the angle 0 like would be right here on a unit circle. 0 is right there. That would be an angle 0. And that point is 1 0. So remember that it's cosine and then sine. So the cosine
Yes.
1
Yes.
and the sine is 0.
And if you switch it, then you have It's
So
like if you switch.
Go ahead.
Sorry. Great. Go ahead.
So if you are just plugging in the 1 in, you have 2 times cosine of 0 is 1 plus 8 times cosine of 0 is 1, and that's going to be equal to 10 then.
10. Okay. I think I am going to go back and review.
Yeah.
The trigonometry, probably on like Khan Academy.
Yeah, that would be good. Just some really basic things just to refresh you on just like some basic definitions. Then you should be good to go. All right, let's look then at the next section. So this is going to be section 1.5, and this section is about limits at infinity and infinite limits. All right, so let me just tell you, this is going to be important in this section. So in this section, there's kind of the standard trick that we use when we're finding these limits. And this trick is going to be to divide the numerator and the denominator by the highest power of x that appears in the denominator. So that's the
Okay.
standard trick that we're going to use in this section.
Okay.
So let me do kind of a basic example here. Like, let's say that we want to find the limit as x goes to infinity of 2x to the sixth power plus 6x to the fifth power plus 4 divided by 9x to the seventh power. So what is the first thing that you always try to do when you have a limit?
The first thing you try to do when you have a limit is
Like, what were we doing
to see if we can fit it into close to a theorem. Get
So
it
we can
to
try to use one of the theorems and try to do something,
okay.
or we can try to just plug in a number that we're given, right?
Oh, put it as well. See if we can put in 0 first.
Whatever the number is, like whatever
What?
this x value is here. So
Okay. Oh, yeah. Okay.
now we have something that's a little bit different. Like we have x going to infinity. We don't have a specific number, but we have a number that's really, really big. Like what happens is x starts getting really, really big
Okay.
to this function. And
Mm-hmm.
we could kind of do this intuitively and maybe just plug in like really big numbers and kind of see what's going on, see if we can figure this one out.
Mm-hmm.
Or, there's no algebra really. We could do division here and do each one separately, but it's not really going to help us. But when you have limits that are going to infinity, this trick works when x is going to infinity. Our trick is to divide the numerator and the denominator by the highest power of x in the denominator. So what is the highest power of x in the denominator?
7.
Oh, what did I just do there? Let's see. Oh. Okay, okay. So it's 7. So we're going to divide everything we're going to divide the numerator and the denominator by x to the 7th power. So not just that 7, but everything is going to get divided by x to the 7th power. So I have 2x to the 6th divided by x to the 7th plus 6x to the 5th divided by x to the 7th plus 4 divided by x to the 7th. That's our numerator, and the denominator is x to the 7th. So we have that. So everything in the numerator gets divided by x to the 7th. Everything in the denominator gets divided by x to the 7th.
Okay.
Okay? Let's
Mm-hmm.
simplify then. Simplify. Limit as x goes to infinity. 2x to the 6th divided by x to the 7th is equal to what?
2x.
So 2 over x, right? And then 6x
Uh,
to the 5th?
the x's. Did the oh yeah,
Yeah, they
2
cancel.
over x. Yeah, sorry, I was doing a.
Yeah, so 6 of these
Yeah,
cancel with 6
yeah,
of those.
yeah. I got it now.
Okay.
Thank you. I'm sorry.
Oh, you're fine.
Okay.
And then 6x to the 5th over x to the 7th.
6 over x squared.
Yeah, I'm going to rewrite this down here so I can write a little bit bigger.
Okay.
So we have 2 over x plus, and we have 6 over x squared. And then we have 4 over x to the 7th. We can't really simplify that. And then let's take a look at our denominator. What do we have in our denominator?
9x to the 7th over, no, we just have 9.
Yeah, because those x's are
Yeah,
going to cancel,
yeah,
so we just have 9.
yeah.
So now we're going to look and see what happens to each one of these things in the numerator. Like, what is 2 over x? Because we're looking at what the y value is, and we're kind of looking at what this thing is getting close to. It might not always be a number. Sometimes it's going to be a number. Sometimes we'll see. So, like, if I have 2 over x, let me just write this one as, like, let's say this is an individual one. Limit as x goes to infinity of 2 over x. So this means as x gets really, really big, like what is 2 over x going to be? So if you have if you have a calculator and you plug in like a big number, like let's just say you start off with 2 over 100, for example, that's going to be 0.02. What if you do like first is going to be 0.02. What if x is 1,000? Like what if you do 2 divided by 1,000?
Oh, then it will be 0.0002.
Yeah. And if x is 10,000, it's 0.0002. And you can see like what's kind of going on here. Like what is
Yeah, yeah.
Yeah. So what is this approaching then? What is the y value?
So the y value is it's approaching zero, but it's
Correct.
not hitting zero, intersecting
Exactly.
with zero.
So it's not exactly zero, but we say that the limit is zero because we're looking at it's getting, close to. It's pretty close enough. It's close enough to zero that we're just going to say that it's equal to zero. So as we make
Okay.
x get really, really big, this limit is
Mhm.
equal to zero. So this thing here is going to zero. What about 6 over
Okay.
x squared?
So it would be pretty much, it'd be the same.
Same thing, right? That's going to zero.
Mhm.
4 over x squared, that's going to zero also.
Mhm.
So what is this limit going to be equal to then? We got 0 plus
Uh,
0 plus 0 over 9.
so it'll be zero.
Yeah. So that's going to be equal to 0. So that limit is going to be equal to 0.
Okay. Okay.
All right. Let's try one that's similar but is a little harder. So let me insert another page here. So this is another problem. Let's say we have limit x goes to infinity of 8 times the square root of x cubed minus 8x divided by square root of 6x cubed. Okay, that looks like a good problem, right?
Okay.
Um,
Yeah.
all right, so we look at this and we see that x is going to infinity. Like there's not a lot of algebra that we can do. We can't factor anything or cancel anything, divide by anything. X is going to infinity, so we can use that same rule that we had before, but we probably want to try and rewrite this in a way that makes a little bit, that might help us out a little bit, because if
Okay.
we look at the denominator, like what is the highest power of the denominator? It's a little bit tricky the way that it's written, right?
Right.
So
Mhm.
yeah, what is it clear like what the highest, like what the denominator power is?
Um, well, if it has a square root over it, doesn't that change it from being three? Or
So,
do we count three as being the highest
yeah,
power?
that's the question,
Okay.
right? Like how are we
Okay.
going to do that?
Yeah.
So let's just try and rewrite that. Like if you have a square root of something,
Okay.
like if you have like a square root of 2 times 4, for example, you can write this as the square root of 8, or you could separate it
Mhm.
as the square root of 2 times the square root of 4. You can
Yes.
separate things that
Okay.
are multiplied. You can't do it if you
Mhm.
have addition. Like if you have this, it's not equal to the square root of 2 plus the square root of 4. You can only separate things with multiplication. So we can
Okay.
separate that denominator and write it as the square root of 6, which is just going to be a constant. We can kind of ignore that, times the square root of x cubed. Okay?
Okay.
And then let's take a look at the numerator. The numerator looks kind of similar. We have this 8, and then we have the square root of x cubed. I'll just rewrite it and we'll do the same thing on the next step. Okay. So I'm not doing anything to that numerator.
Okay.
So then we have the limit, x goes to infinity. All right, now let's take care of those square roots of x cubed. So square root of x cubed, square root of x cubed. If I say, like if I have the square root of x, how do we rewrite the square root of x? It's x to what power?
To the um what it's a fraction, but I
Yeah,
don't remember.
to the 1/2
Yeah.
power.
Yeah.
So you know that because square
Yes.
root is, the power is
Yes.
1/2 on that.
Yeah.
Yeah. So you can do the same thing with x, the square root of x cubed. It's x cubed to
Yes.
the 1/2 power. So really that's x to the 3/2 power. So the square root of
Okay.
x cubed is really x to the 3/2 power. So let's rewrite it that way. We have 8x to the 3/2 power minus 8x divided by the square root of 6 times x to the 3/2 power. That's the same thing there. Okay?
Mhm.
And I know that I'm going super fast. Like if I was really
I'm
teaching, I
keep,
wouldn't go this
yeah,
fast.
I can keep up with you.
Okay, good.
So that's
Um,
fine.
because I know I'm not giving you a lot of time to process anything.
No, but, and I
It's a
can
lot
go
of
back over
stuff.
this and review. So
Yeah.
that'll
Okay.
be good.
So then we're going to use that same rule that we used before, where we're going to divide everything by the highest power of the denominator. So in the numerator, we have 8x cubed, or yeah, 8x to the 3 halves, and we're going to divide that by the highest power of the denominator. Has to be x to the 3 halves, right?
Hmm.
Okay.
Okay.
Minus 8x divided by the highest power of the denominator, x to the 3 halves, divided
Okay.
by,
So, so we're at the square root of 6 again.
yeah,
So that hasn't changed.
nope, that just
Okay.
hangs out. Don't do anything with that. All right, so everything gets divided by x to the 3 halves power.
Okay. And
All
so
right,
we'll cancel out the x to the 3 halves on the denominator.
yep, those
And
get
then,
canceled.
and then, yeah, that one. Yep. Okay.
So as x goes to infinity, in the numerator we have left 8 minus, and then we have that 8x over x to the 3 halves. So 8x over x to the 3 halves divided by square root of 6. So we have to think about this thing, what's going on here. So as we make
Hmm.
x get really, really big, we have 8
Mm.
times x in the numerator, and we have x to the 3 halves power. So the denominator is bigger because it's 1.5. Like the numerator was 1, 8x to the first
Okay.
part.
Okay.
The denominator is
Okay.
something bigger. So just like before where we had 2 over x squared or 2 over x, that denominator is bigger. So what is that numerator, that part going to, that 8x over x to the 3 halves?
Um, that is ap approaching 8.
So if you make
Oh,
x, well, like look at this
no,
example
no.
here from the
Okay.
last example, 2 over x
Uh-huh.
squared. Like when we make that denominator get really, really big, like 2 over, a million,
Mm,
what
hmm.
is that equal
Okay.
to?
Okay. So it's going to be 0
Yeah, it's going to be 0
again.
because that denominator is going to be getting much bigger than the numerator. The denominator is getting really, really
Uh,
big,
yeah.
and the numerator isn't going to be as big. So that's going to, in the long run, as we keep making x get really, really, really big, that's
Hmm.
going to go to 0. So this limit then is going to be 8 over the square root of 6.
Okay. Okay. Because that there's nothing more we can figure out as far as where it's approaching an. I'm going to review this again and
Oh,
start
you're
again.
fine. You're fine. Yeah, the only because all we're left with is numbers here. We're just left with this number
Yeah.
and this number. So there's
There's
nothing to
nothing
do with
else
the
we can.
numbers. Yeah.
That,
So we're
that's okay.
just
That is where I was going.
yeah,
So that's good.
because
Okay.
we're trying to get rid of as many powers as we can so that we can
Yeah.
be left with those things that are equal to 0. That's why we divide by the highest power to get rid of those things, and we're just left with those
Okay.
zeros.
Okay.
All right, so let me see if there's anything else in here that might be a little challenging. Let's see, maybe. All right, so this section is called limits at infinity. So we've done limits at infinity, like x goes to infinity. We've done 2 of those. And it's also about infinite limits. So let me show you an example of what that means. Suppose you have the limit as x goes to -3, and we're going to go from the left of x
Okay.
squared over x plus 5 times 3 plus x. All right, so this one isn't a limit at infinity. It's not x, as x approaches infinity like the other one. So we don't have that nice little trick like we do before where we can
Mm-hmm.
divide the top and the bottom by the highest power of the denominator. We don't have that trick anymore. So instead, let's go just kind of back to where we originally kind of started by plugging something into the function, right?
Okay.
So here we're x is approaching -3. So the number that x is approaching is going to be -3, and it's approaching from the left. But what happens if you plug -3 into the function?
So we'll have 9
Just look at
over
always
if
just
you
look at the
it's like
denominator because we don't really care about
okay,
the
okay,
numerator.
okay. Um, and you'll have 8 basically on the denominator.
So
And
if you plug a
the
-3 in here, you have -3 plus 5.
negative 3. Oh no, it'll be 2. Sorry, it'll be 2, and then the 3 will cancel out. The negative 3 will cancel out the other one.
So when you say cancel out, what does
So,
that mean though? If you plug in a
or,
-3?
or if, or sorry, if you do 3 plus -3, you'll end up with 0,
Correct.
and then you'll end up with 0 in the denominator,
Yeah,
and then your whole denominator will be 0.
exactly. And that's a problem then. So we
There
know
we
that
go.
we can't plug in that -3.
Okay.
So can't plug in -3. But we're not going to say, that this limit doesn't exist just because we can't plug it in. Maybe we're going to try to do some algebra. But if we did algebra, like if we foiled these things, we would just be left with like x squared plus 15 plus 8x, which really isn't going to help us out that much because if we plug -3 in, we'll still have a 0 in the denominator. So can't plug in -3. What we're going to do instead
Okay.
is let's find out what happens. Let's see what happens when we check numbers. Oops, sorry, that is really messy. When we
No.
check numbers close to -3, because this is saying as x approaches -3
Mm-hmm.
from the left, it's getting close to -3. It's not exactly -3. So if we look at a number line, if we have like -4, negative, I'll redo that. If we have, let's say this is -4, and let's say this is -3 and -2. So we're approaching, getting close to -3 from the left-hand side. So we want to look at numbers that are like really close to -3.
Okay.
So for example, like a number that would be close to -3 would be, but that's, on the left of -3
On
would
the
be like
left. Mhm.
negative 3, -3.1,
3.5. Mhm.
negative
Okay.
3.5, then -3.4, -3.3, -3.2, -3.1. We could even get closer. We could do -3.01 or -3.001. And we can just keep getting as close as we want. And let's see
Okay.
what happens when we plug in one of those numbers. And maybe we can do it more than one time too. So as x approaches 3 from the left, let's see, what do we want to pick? Let's say that we plug in um, negative, maybe try this one. Or maybe we'll just let's do this one, -3.001. Let's plug that in. So we have
Okay.
-3.001, and that's in the numerator. We want to square it.
Okay.
Then in the
Okay.
denominator, let's see what's happening. If we have -3.001 plus 5, and I'm just plugging that number in, times 3 plus -3.001. Okay, we can kind of think about what's going on here
Mm-hmm.
and kind of get our answer after we've maybe done a few of them. But
Yeah.
since we haven't done a few of them, let's plug it into our calculator and see what's going on. So limit as x approaches 3 from the left. So -3.001 squared. Do you have a calculator?
I I'm plugging it into my calculator on my computer right now.
Okay. So You don't need to plug in the negative because you're just going to square. It's going to be a positive number. So 3.001 times 3.001. So I just plugged it into my phone and got 9.006001.
Yes, that's what I got.
And then in the denominator, we have two numbers. So we have negative 3.001 plus 5. So negative 3.
1.99.
Okay, so 1.999, right?
Yes.
Times,
Okay.
and then 3 plus 3.001 or 3 minus 3.001.
And then it'll just be 0.001.
And it should be a negative number because it's 3 minus something
Negative.
teeny tiny bit bigger. So negative
Yes.
0.001. Yeah.
Okay.
So you can see in the top we have a positive number, and in the bottom we have something that's going to be a negative really, really, really small. So I don't really need this limit here either. So the top we have 9.006001, and the denominator, when you multiply those two things, 1.999 times negative 0.001, you get a negative, and it's going to be like a really small number. 0 point.
Mm-hmm.
What do you have?
0.001999.
Yeah. Okay. So now if you take 9, it's close to 9.006001. And we're taking 9 basically, and we're dividing it by a really, really small negative number. So if you have a number divided by a really, really small number,
it's got to be close to 1. No.
So
No.
Put it in your
Okay.
calculator and see.
Okay, thank you. Okay. Well, no, it's really big. Yes.
Yeah, it should be a really
big.
big number,
It's really,
right?
really big.
It's like it does the opposite of. It's kind of like the reciprocal. You take a number, you divide by something that's really, really small, it makes that number really, really big. So it makes it really big, so it's like it's just going to keep getting bigger and bigger and bigger if we keep getting closer and closer to that negative 3. Like if I did 3.0001 and plugged it in, it would still get bigger and bigger. So it's infinity, but the negative in the denominator makes it negative infinity.
Negative infinity. Oh, okay.
Okay?
Okay. Yes.
All right. Then
any answering you throughout your time with me tonight, you were every time you write out the limit of x approaches as x approaches, the number, is that something? It just seems like the standard thing to do. Like if you're instead of writing x equals, you're just doing that. Like it.
yeah,
I don't know.
you should always be saying
it?
like x, because x doesn't equal it. I always have this arrow saying x approaches negative 3. So we want to make that distinction because we're not saying, like in this example, we're not saying x is equal to negative 3. It's getting really close to negative 3. So yeah, we always write that notation.
Just a kind of like a nice reminder, not a reminder, but just a standard way of
right, exactly,
expressing it.
Yep.
Okay. Thank you.
You are welcome. And let's see, let me get another page here someplace. Let's find maybe another. This section has another topic to it. This also talks about asymptotes, vertical and horizontal asymptotes. So if you took Math 136, if you've had recently college algebra or pre-calculus, you should have talked about asymptotes in that class.
Yes, I do recall that.
Okay, so vertical asymptotes. We have a definition in calculus, and we say that x is equal to c, where c can be like any number, is a vertical asymptote.
Okay.
If either of these things occur, and I might not write them all out, if you have a limit as x approaches c, And this could be from the left or from the right of our
Okay.
function. It can be from the left or the right or just c. And that's going to be equal, and it could be positive or negative infinity. So if the limit of a function as it approaches c is equal to positive or negative infinity, that's going to be the vertical asymptote. X is equal to c. So let's look at an example.
Okay.
So for example, let's say we have this function f of x is equal to 1 over x minus 2. And if we were to graph this function, I'll just graph this function. So in college algebra, we learned how to graph these rational functions. But we saw that, well, actually, let me do it this way first. I'll do it the calculus way. The calculus way says limit as x goes to c, and here our c is going to be 2 because that's where our denominator is not defined. Denominator is not defined at 2.
Okay.
Um, and so I'm going to say of the function 1 over x minus 2.
Okay.
All right, so if I plug in, we know that we can't plug in a 2,
No.
but we can plug in something that's really close to 2, like really getting close to 2, like 1.9, 1.999.
Okay. And then I'll just turn it into the denominator into a negative.
Well,
Or
depending
no.
upon whether I'm going from the left or from the right.
Oh, right. Okay. Okay.
So let's say I'm going from the left again, like 1.9. Like let's say I plug in 1.9. Like what's happening in the denominator? Like if I plug in 1.9 and 1.99 and 1.999, what is the denominator getting close to?
Um, it's getting close to 0.
It's getting really, really close to 0, but maybe it's like 0.0001,
Mm-hmm.
or maybe it's 0.00001 or 0.0001. So what is 1 divided by 0.0001 or 1 divided by 0.0001?
So it's really close to 0.
The denominator is
No,
close
no,
to
no, no,
0.
no, 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 no. No, it's a really big number.
Exactly. It's a
It's
really big number.
infinity.
It seems weird, right? Because you have these like tiny numbers. Where's this infinity coming from, right? It just doesn't seem right. But yeah, I
Oh,
mean, you
this
can
is yeah.
do it on your calculator and see. So that's the calculus way of finding asymptotes. In college
Okay.
algebra, we had this function and we said vertical asymptotes. It's kind of easier to do it the college algebra way because college algebra way says the vertical asymptotes are the vertical asymptotes. I'll say this is or. So this is calculus way.
Okay.
Calculus way. College algebra way says vertical asymptotes occur where the function is undefined. So they occur where the function is
Mm-hmm.
undefined,
Mm-hmm.
where the denominator is equal to 0. Undefined. So they occur where x minus
Yes.
2 is equal to 0. So we know that that's x is equal to 2. So we can just look at that thing and see that the vertical asymptotes are going to be, there's going to be a vertical asymptote at 2 for this function. So you should have done that like in college algebra or
Yes.
pre-calc,
Yeah.
finding those vertical asymptotes. All right, then if we want to find the horizontal asymptotes, there's a calculus way. So this is our college algebra way. All right, let's look at horizontal asymptotes. Horizontal. Again, we have a calculus way and a
Mm.
college algebra way. The calculus way for horizontal asymptotes is actually a little easier. This one says that y is equal to b, where b is just some number, is a horizontal asymptote if now we're looking at a limit at what's happening when x goes to infinity, as x gets really, really large. And if whatever that b is, that's going to be our asymptote. So if we
Okay.
have the same function, f of x is equal to 1 over x minus 2, let's just see what happens when we make x get really, really large.
Okay.
So now we have x going to infinity. We can use that one trick that we did before. Do you remember what the trick was when x goes to infinity about how to find this limit?
When um, mm,
You can divide everything.
yep, got it. I got it. I got it. I got it. So you can divide it by the highest power of the denominator.
Correct. So the highest power of the
Yeah.
denominator is?
1.
Yeah, it's going to be 1. It's x to the first power. So we're going to divide everything by x to the first power. So what is this then? Now we're making that denominator get really, really big, not really, really small like before. We just were making it get small. Now we're making it get really, really big. 1 divided by a really, really big number is the opposite of what you might think.
So rather than go on my instincts, I'm actually just gonna like
it's the
put it on
opposite
the
of your
calculator.
instincts, trust me.
So it's a really, really small number.
Exactly.
No.
Exactly. Yeah, it's the opposite. Like 1 divided by something really, really big is something really, really small. 1 divided by something really, really small is something really, really big. It's the opposite.
Okay.
All right. So that's 0 divided by, this is a 1 in the denominator. So that's 0 divided by 1 minus, and then this thing goes to 0 also. So 0 divided by, oops, that's a 0.
Okay, so it's
So that's a 0.
0 again.
Okay. So that's the calculus way of doing it.
Okay.
So that's it's not too bad. It's actually pretty easy. The college algebra way, we had to memorize some rules for it. If we had this function f of x is equal to 1 over, and you don't have to use this way, but we had these rules that said if this is a proper fraction, if it's proper, for example, like a proper fraction, like 2 divided by 3 is a proper fraction because the degree of the numerator is less than the degree of the denominator. This is proper. And anytime you have a proper fraction, the rule is that it's always going to be y is equal to 0 for the horizontal asymptote. Oh, I forgot to say that over here. That was the horizontal asymptote here. So
okay, and that's the right way to express the standard way to express that. I just want to make sure.
Yeah, the horizontal asymptotes. They're equations. Yeah. Y is equal to something because it's a line. So if we go back up here to the graph, y is equal to 0 is this horizontal asymptote at the x-axis.
Okay.
And then when you graph this function, it looks like this. We have this asymptote here, this asymptote here. There we go.
Okay.
Okay. So those are the finding asymptotes. Just another part of this section.
So I always thought of asymptotes as kind of just like an axis that's shifted off of the origin. So is that an okay way to think about it?
It's not really, I mean, it could be a shift depending upon the function that we're starting with. It's okay to think about it that way. But the main part is that you really want to think about these asymptotes defining where the function is going to lie, because if we have an asymptote here, asymptote here, the function is going to be approaching those asymptotes. It's not going to cross over those lines. It's just going to approach it and get close to it, but it's not going to cross that vertical asymptote at all.
Okay.
So try to think about that.
Just kind of defining the boundaries of the function.
Exactly. All right. Okay. Then let's do let's talk quick about section 1.6. And 1.6 is about continuity. All right. So we have a definition of continuity. So do you have your book open to that section?
Yes.
Okay. So continuity at a point. So I'll talk about continuity at a point and use this definition. So let f be defined let f be defined on, and this should be one of the first things in your book, probably that first page, on an open interval containing C. Then f is continuous at C if if the limit as x approaches c of f of x, if the limit of that function is the value of the function f at that number c, whatever that c is. So this requires three things to happen. So this statement that I just wrote above is the same thing as saying that the limit exists, the limit as x approaches c of f of x exists,
Okay.
and f of c exists. That just means the value of the function is defined, exists,
Okay.
and the limit as x approaches c of f of x is equal to the value of the function at c. So we need those three things to happen. So really
Okay.
we're looking for a function that we can draw without having to lift our pencil off the paper. So like this function here
Okay.
is definitely continuous. But if I
Okay.
draw a function that looks like this, I can't draw that without lifting my pencil. So that one is not going to
Okay.
be continuous. So that's just a couple
Okay.
examples. Um, let's see. So what if we say, is f of x, is this function, this is just going to be a really basic one, x minus
Okay.
9 times x minus 8, is that continuous at x is equal to, at 9, and x is equal to 9. So is that continuous at 9? So in order to find out if it's continuous, we have to check these three conditions. It has to pass all three of
Okay.
those conditions. So the first one says
Okay.
the limit as x approaches c of f of x exists. So that's the first one. So we have to see if that limit exists. So we're looking at the limit as x approaches, and they're telling us 9 right here. We're specifically concerned about 9, so that's what our c is going to be. So as x
Okay.
approaches 9, and our function is x minus 9 times x minus 8. So does that thing exist? So find that limit in the usual way, just by plugging in the 9.
Mhm.
And what is that
And
going
then
to
you'd
be?
end up with one. Oh, no, 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 no. That's going to be 0.
Yeah, it's going to be 0 because it's going to be 0 times 1. So it's going to be equal
Hmm.
to 0. All right, so it passes the first test. So we're going to check the second test. So the second test says f of c exists. So we just want to make sure that the function is defined at that point. So f of c, c is 9.
9.
So we want to find f of 9. So f of 9 means you're going to take the function, this function f, and you're going to just plug 9 into the function.
Okay.
So what happens when
So
you plug 9 into the function?
we end up at 0.
Yeah, you get the same thing. You get
Hmm.
9 minus 9 times 9 minus 8, so 0 times 1. So you get the same thing. And
Hmm.
then the third
Um,
rule says the limit as x approaches 9, well, as x approaches c of f of x, has to be equal to f of c. So in our case, we're saying the limit as x approaches 9 of f of x has to be equal to f of 9. And we just calculated these two things above. We already did this one. We said this one
mhm.
was equal to
Is
0, right?
0. And the f of 9 is equal to 0.
So they're equal to each other.
Okay.
So therefore, this function is continuous.
Continuous. Okay. Okay. That makes sense.
So if any one of these, if any condition is not met, if it
Hmm.
or any test is not met, the function is discontinuous.
Okay.
Discontinuous at that point, at whatever point we're talking about. So if it's not continuous, it's discontinuous. All
Okay.
right, so let me do another example. So is this function is f of x equal to the absolute value of x minus 5 over x minus 5. Is this continuous at 5? Okay. So we have
So,
to go through all three of those steps,
mhm,
just like we did before. So we want to know, like, what is the limit as x goes to c of f of x? That has to exist. So in our example, our c is 5. So limit
mhm,
as x approaches 5 of the absolute value of x minus 5 over x minus 5. All right, for this one is, since it has this absolute value, it's a little bit weird. So it may be helpful to graph this one. May be
okay.
helpful to graph this and see what's going on. So let's say if we make a table. And we're kind of interested in values like around 5 because 5 is kind of like the significant number here. So
Mhm,
let's say that we plug a 5 into our function. So we're looking
okay,
at
okay.
absolute value of x minus 5 over x minus 5. If I plug in a 5, the numerator is a 0, denominator is a 0. It's really undefined at 5, right? Because you can't divide
Okay,
by 5. So let's pick something else around 5. Like let's just try to start with 6.
okay.
So if you plug in a
So
6,
denominator is going to be 1. Um, and now I do you have to look at it. It's always going to be positive. The
yeah,
answer is always
yeah,
going to be positive. So it's just going to be 1.
yeah, it's going to be 1. And what if you plug in a 7?
It'll be 2. Or no, it'll be 1.
It'll be 1. And if you plug in an 8, it's going to be a 1, right?
Same. Yeah,
And then,
yeah.
what's going on between 5 and 6? Like if you plug in like 5.5, what if you plug in like a 5.5 or something like that?
Um, it it'll be the same.
Yeah, it's still going to be 1.
It's still
So
going to be 1.
at
Yeah.
5, it's undefined. Like we don't really know what's going on at 5, but as we get really, really close to
Okay.
5, they're all going to be 1s as we keep getting bigger. Like 5, 5.1, 5.2, they're all going to be 1s. The y values are all going to be
Okay.
1s, right? All right, let's see what's happening when we go to the left of 5. Like let's try 4, for example. If you plug in a 4, the numerator is
The numerator is going to be 1.
1 and the denominator is
Going to be negative 1.
negative
So we're
1.
at a negative 1.
Yeah, so it's negative 1. And at 3,
So 2 over negative 2. So negative 1 again.
yeah, and so they're all going to be
Yeah.
negative 1s. So as we go like 4, 3, 2, 1, 0, everything is going to be a negative 1. So let's say this is negative 1. Everything is going to be a negative 1. It's not defined at 5, so I got to put a circle there.
Okay.
So it just can't be defined at 5. Like it just can't isn't defined at 5. So if we go through our limit rules, um, what can we say about the limit as x goes to 5 of the absolute value?
It's undefined.
Yeah, it's undefined. That limit doesn't exist because you can see like at 5, it doesn't exist at 5. We can't draw this function without lifting, our pencil to
Yes.
draw it. So you can tell by looking at it that it can't be
So it's a
continuous.
discontinuous.
Yeah. So does
Uh,
not exist. This does not exist. And also, if we do that second step, if we try to define f of 5 by plugging that into the function, I'm just going to write DNE for does not exist. That does not
okay.
exist either. So the limit doesn't exist, the function doesn't exist, so this one is not continuous.
Okay.
Okay?
Okay.
And let's see. Oh, do you want to do one last problem? I know I'm kind of going over the time a little bit, but there's just one last one. Do you have time to do it?
Sure.
Okay.
Yeah, yeah, I do.
So this one is just a little bit different. So that's why it might be helpful to do this. So this will be like
Okay.
the very last problem that we do, and then we'll cover 6
Okay.
sections. That's a lot. Well, actually, it's 5 because
Yeah.
about that one. which is a good thing, trust me. All right, so let's look at this function. F of x is equal to 3x squared minus 12 divided by 2 minus x is not defined at, where is this not defined?
2 minus x at 2.
Yeah,
X equals 2.
correct. It's not defined at 2. So, because it makes division by 0. So the question is, how should it be defined in order to make it continuous at 2? So what we have now is we have some function where something is happening at 2. Let's say this is 2, and it's not defined at 2. There's some open circle. We have something going on. It's not defined at 2, so it's not continuous, but we want to figure out what is that value? How can we define it specifically at 2, where we're going to say when x is 2, what is our y value to make that function continuous? Okay, so we know that in order for it to be continuous, it's continuous at c if the limit as x approaches c of that function, we know this by our definition, is equal to f of c. We also, yeah, that's just our definition of continuous. So we know that this function is discontinuous at 2. So what we're going to do is we're going to find the limit as x approaches 2 of our function, because we know that it has to equal f of c. So this is the limit as x approaches 2 of 3x squared minus 12 divided by 2 minus x. So we're going to find this limit. So we know that we can't plug 2 into this function the way that it is, right? But we're going to try and do some algebra on it like we did before. So the limit as x goes to 2, and in the numerator, let's factor a 3 out of the numerator. So we have 3 times x squared minus 4. What was that noise?
Oh, I don't know.
Did you hear that?
I
don't know. Maybe
might have had some. I've had the headphones in my ears, so I can't hear as
and
much
it was
here,
like a computer thing. I think it was my computer, but I just don't know what the sound was. So in the denominator, instead of writing 2 minus x, I'm going to write it as minus x plus 2. That's the same thing.
Okay.
And then limit as x goes to 2 of 3, and then I'm going to factor that x squared minus 4 as x minus 2 times x plus 2 divided by minus x plus 2. And then you can see that we can almost cancel something out. Can't quite cancel x plus 2. But what we can do, I'm just going to copy that numerator. I'm just going to factor a negative 1 out of the denominator. If I factor out a negative, it's the same thing as x minus 2, right? Because if I distributed that negative, I'd get negative x plus 2. Then I can cancel these two things.
Okay.
And then I don't have that denominator anymore. I just have that negative. I can put the negative in the numerator. And then I can plug that 2 in, and I can move the negative up to the numerator. And I have negative 3 times 2 minus 2. No. It's plus, right? Oh, I canceled the wrong one.
Okay.
Is that what you were looking at?
No, I was working it through on my computer.
Yeah. All right, so negative x minus 2. So then this is what I had before, but I canceled the other one instead of this one. Okay. Then this becomes a plus. Okay. And then that's negative 3 times 4, which is negative 12. So this is asking us how to define this. So what we're going to do is we're going to define f of 2 specifically to be equal to 12. And then that's going to make this function continuous. So like on this picture that I drew, which isn't really the graph, but like if this were a 12, and I would say f of 2 is 12, then I could fill that circle in and make that function continuous.
And so just at the very end there, you did lose me. When you worked it through algebraically, it's a negative 12. Did you do anything else to define f of 2 as 12, a positive 12?
No, so what I did,
No, no.
so when I got to this point, I just plugged 2 into that
Uh-huh.
function. Were you okay with that? Like I just took 2 and I plugged it in
Okay.
to get this
For what? But negative. I'm just wondering why
with a negative in
ne
the denominator?
the the negative 12 that you got when you multiplied negative 3 times 4,
Yeah.
when you have f of 2 equals
Oh,
12,
yeah, that should be a negative.
is that
So,
it should be okay.
yeah, that
Okay,
should
I
be a
didn't know
negative.
if there was
Thanks.
some implied function
I was just thinking about my graph here.
operation. No,
Like my
no,
graph.
I was thinking it. I was like, that is a positive, so that makes sense. So I thought maybe
Yeah.
I was. Um,
I wasn't trying to draw the function in the beginning, like the actual function. It was just an example. So,
yeah,
yeah,
that
but
makes
that's the
sense now.
concept of, how you
Okay,
would define it. We would define this to be negative 12 in order to make that thing continuous. But yeah, that should be a negative. So thanks
okay.
for finding that.
Oh yeah. Okay.
All right.
Yeah, this will be. I had math camp last summer, so I need all the remediation I can get here. So, but this,
All right. Do you have any other
well,
questions?
um, just how will I access that again? Do I have to come
I
back
don't
here?
know. I'm going to
Okay.
see after I finish this. I'm going to see what I can do with it. So
Okay.
I haven't done this before, so I am going to see where I can put this. And I
Okay.
don't know if I will have a link to like because I don't think I can put it right in Ivy
Uh,
Learn. I'll probably have like a link to a YouTube or something maybe. Probably do that.
okay.
We'll see. I'll
Okay.
see what I'll do with it. I'll let you know. I'll send.
Okay.
Yeah, I'll let you know.
I appreciate it,
Okay.
and thank you very much. Will you be here next week?
Yeah, I am
Or
planning
okay.
on doing this on Wednesdays. I thought there would be more people here today. So I
Mhm.
don't know if that's because today is like Wednesday's a bad day. So if anybody else responds and wants a different
Mhm.
day, then we'll
Mhm.
see how we can go. Somebody had suggested Friday morning, but I don't know if that works
Okay.
for you or not. I'm just going to sign off on this right here so I finish this.
Sure.
But
Yes. Yeah.